In the last lesson, we derived an infinite series expression for e to the x using the binomial expansion. It turns out the Taylor series expansion gives us the same result, seen in the last line. We use this polynomial to evaluate e at a non-integer exponent. That is, we plugged in a value of x that is not an integer. Today we are going to further explore that idea. Suppose we wanted to evaluate e to the 3.28. To do that, we could take 3.28 and plug that in for x in the Taylor polynomial. That value is shown in the last line. The red digits are uncertain. Here is a spreadsheet showing that calculation. Notice in the rightmost column the digits underlined in red. If you look in the row immediately above that, the digits are all different, which makes me rather uncertain they are correct. However, 26.57 occurs for both n equals 11 and n equals 12. Furthermore, in the fourth column, we see 2 zeros past the decimal, as underlined in purple. This indicates our answer of 26.57 cannot have converged any more than 2 digits past the decimal. Before we move on, take note that after 13 terms, we have only converged to 4 digits of accuracy total. Is there a better way to do this? Yes, we are using 3.28, which is greater than 1. This data table and graph demonstrates that any number greater than 1 grows as we exponentiate it, as seen in orange for 1.01. Meanwhile, any number less than 1 gets smaller when we exponentiate it, as seen in blue for base 0.99, which is smaller than 1. To maximize the efficiency of the series expansion, it is best to make our argument less than 1. That will cause faster convergence. Then we can use laws of exponents to get the number we want. So let's take a look at this again. Using laws of exponents, e to the 3.28 is the same as e cubed times e to the 0.28. We have already calculated the value of e to 14 digits past the decimal, so there's no need to do that again. E cubed is that number multiplied by itself twice. The answer is boxed in orange. To get e to the 0.28, we can plug 0.28 into the Taylor polynomial. The answer is underlined in blue, with uncertain digits in red. Here is the spreadsheet of that calculation. In the rightmost column, look at the digits underlined in blue. If you look in the row immediately above that, all those digits are the same. It is the last 3 that are different. To further support my case is the fourth column. Underlined in purple are 12 zeros past the decimal. That indicates my answer in blue cannot have converged more than 12 digits past the decimal. So now let's multiply those two numbers together. Our final answer is shown in the last line. The value underlined in blue limits the digits of accuracy in my final answer. The uncertain digits are in red. Now compare this calculation with the true value, which can be easily obtained by punching in the numbers on a scientific calculator. It turns out we were quite close, and in this case my evaluation of the number of uncertain digits may have been overly conservative. Now let's try e to the 27.84. This is much larger than 1, and if I plug it directly into the Taylor series, I would need many terms before it started to converge. I'm not even going to try that. Instead, we're going to approach this like the last example. First is e to the 27th power. 27 is equal to 1 plus 2 plus 8 plus 16. Using repeated multiplication and laws of exponents, we can compute that number with only 7 arithmetic operations instead of 27. The answer is boxed in pink. Notice how large it is. Even though the base e is not a big number, about 2.7, exponential growth has made the answer very large. Now we can plug 0.84 into the Taylor series. The answer is underlined in blue, with uncertain digits in red. Here is the spreadsheet of that. Again, notice the digits underlined in blue all match the numbers in the row immediately above them. Furthermore, In the fourth column, there are 7 zeros past the decimal, so that puts an upper limit on my digits of accuracy. It turns out we can get more than 7 digits of accuracy if we use laws of exponents to help us out. 0.84 is the product of 0.21 and 4. 0.21 is much smaller than 0.84, so I would expect this series to converge much faster. Indeed, the numbers underlined in dark red and blue support this prediction. Here is the spreadsheet for those numbers. Notice how much more quickly this converges. We get many more digits of accuracy. Now to get e to the 27.84, we must multiply our two previous answers together. That final value is shown on the last line of this slide. Compare that to the true value, which once again can be obtained more directly by punching the numbers into a scientific calculator. We were very close. Had we run the Taylor series another 1 or 2 terms, we might have avoided round-off error in the last digit. That's all well and good for base e, but what if we want to exponentiate a different base to a non-integer exponent? In the example seen here, we want to find 2 to the 3.761. We already flirted with one approach in a previous lesson. Stay tuned for the second half of this lesson, in which we will explore another approach to obtain the answer. Thanks for watching. I look forward to seeing you again.